Okay, for this next screencast, we're going to talk about the second part of Investigation 6A, and I'm going to have these illustrations up, and so you're going to need to read and kind of follow along because the text is not necessarily going to be shown to you. All right, but I'll start you off. We are down here where it says Figure 2 is presented to explore. Figure 2 is presented to explore the roles played by the receipt of solar energy and the Earth's rotation in determining the global atmospheric circulation. And we have three scenarios. Okay, Figure 2A, I'm not going to read all of this word for word, but just kind of follow along. Figure 2A represents a model of an imaginary planet about the size of Earth that has the same side continuously facing the Sun. The planet has a smooth, solid surface and an atmosphere. Okay, if we look at this one, this is Figure 2A, we're talking about a planet that basically doesn't rotate. You always have the same side facing the Sun. So this side is always facing the Sun, this side is always facing away from the Sun. The orange arrows show how the Sun's rays are coming in. Okay, so at the equator of this planet, we're going to get the most direct sunlight. And at the poles, we get the sunlight at such an angle that it's just barely grazing the surface. Okay. All right. It says, going back to the reading, it says the amount of solar radiation received is greatest where the Sun's rays are perpendicular to the planet's surface, meaning the place on the planet where the Sun would be directly overhead, called the subsolar point. Okay, so the subsolar point would be right here, where you're getting very direct sunlight. The Sun is directly overhead. And the amount of solar radiation decreases to zero intensity where the Sun's rays just graze or are tangent to the planet's surface down here at the poles. Okay. All right, remember that because this basically doesn't rotate, half of this celestial object is in perpetual darkness, meaning half of this planet is always dark, and it's always the same side. Okay? Perpetual means forever, unending. Okay, so half of the planet is in perpetual darkness. All right. So now we can go and consider question 3. Atmospheric motion on this figure, Figure 2A, is depicted in the cross-section by the blue lines with arrowheads indicating direction. Okay, so here are your big convection cells that would be set up for this planet that basically doesn't rotate. It's always got the same side facing the Sun. This side faces the Sun, this side faces the way. So we're going to have the atmosphere heated the most here at the equator, and when air is heated, it rises. So it's going to rise, and it's going to move in the upper atmosphere back to the cold side of the planet, and the air in the atmosphere is going to cool back here, and when you have air that cools, it becomes more dense, so it's going to sink. And then it's going to make its way along the surface of the planet, so these are surface winds, back to the warm side, where it will be heated, and it will rise, and it will circulate in the upper atmosphere, back to the cold side, where it cools, sinks, and will make its way back along the surface to the warm side. So there's the circulation. You have one in the northern hemisphere and one in the southern hemisphere. Okay, so just to point this out because it's on the graphic. The subsolar point, remember, is the place where the Sun is directly overhead. Well, we also have an anti-solar point, which is basically on the opposite side of the planet from the subsolar point. Okay, so that's what this is. That's why it's pointed out. All right, so back to question 3. The most intense heating of the atmosphere takes place on the planet's surface at the subsolar point, where the air expands and becomes less dense. At that location, the warm air... Okay, so I'm down here answering the question. The most intense heating of the atmosphere takes place on the planet's surface at the subsolar point, where the air expands and becomes less dense. If the air expands and becomes less dense, then at that location the warm air is going to rise. At the anti-solar point, the temperature is lowest, the air is most dense, and the air sinks. Okay? So that's the circulation that's set up in 2A. Okay? On page 4 of your investigation, this whole paragraph is basically walking you through what I just discussed on 2A, so I'm not going to read this to you. Okay? All right, let's look at 2B, this graphic down here. And I'm going to start reading on your lab investigation right here, where it says the planet Venus. So the planet Venus, which rotates only once in 243 Earth days, spins rapidly enough to distribute heat adequately throughout its equatorial region to cause the rotation poles to become the coldest places on the planet. Okay, so now what they're saying is, let's say we have a different situation. We have a planet that is rotating, but rotating very, very slowly. Even with slow rotation, we get a change in the way everything is set up. Notice that it's rotating enough that the equator, both on the daytime and the nighttime side, the equator or equatorial regions are the warmest areas of the planet, and the poles are the coldest areas of the planet. Again, we have incoming solar radiation hitting very directly at the equator, just barely grazing, hitting kind of tangent at the poles, okay, coming in at a really shallow angle at the poles. So we have the most intense heating here at the equator. Okay. This time, yes, you're still going to get warm air at the equator rising. Okay, so air is heated here, warm air is going to rise. It's going to move in the upper atmosphere towards the coldest spot on the planet, which again, in this case, is the poles. So the air in the upper atmosphere that's been warmed is going to travel towards the poles. It's going to be cooling there, and cooler air becomes more dense and it sinks. So it's going to sink at the poles, and it's going to work its way back towards the equator along the surface of the planet. So these are surface winds coming back down towards the equator, where the air is going to be warmed, expand, rise, and move off in the upper atmosphere towards the poles. Okay? And that's the same in both of these situations. So look at question number 6. The relatively slow rotation of the planet is adequate to cause the axis of symmetry for the atmosphere's general circulation to shift from what it was in figure A until it coincides with the axis of rotation. Okay? With the coldest air at the poles and the warmest air along the equator, surface winds flow from, okay, so remember, these winds are upper atmosphere, these winds are the surface winds. And if you will look at the direction of the arrow, they are coming from the poles and flowing back towards the equator. From the poles back towards the equator. Because remember, at the equator they're going to be warmed, expand, and rise, and it's in the upper atmosphere. The upper winds are what are flowing towards the poles. Okay, but the surface winds go from the poles back to the equator. Okay, and so that's what you need to address on number 6. So it says, with the coldest air at the poles and the warmest air along the equator, surface winds flow from the poles to the equator. Okay. Okay. Then we have figure 2C, and I'm going to go ahead and do a quick screencast for 2C all by itself, and then there will be one more about the there's a simulation that they want you to look at, and we'll look at that in just a second. Alright, so join me for the next part.